Okay, so today we are going to look at Bayesian or Bayesian models and regression models. So already we have looked at Bayesian models for a single or one parameter. We've considered the Bayesian model for a single parameter under the normal distribution, where we assume the normal prior for the parameter mean. And then we also looked at the Bayesian model for Poisson, where we are interested in only one variable, which is the rate of the Poisson random variable. And we assume the gamma prior for the Poisson distribution. That is the conjugate prior. And we also considered a single parameter situation for the binomial random variable. And that we assume the beta distribution for the parameters. Today, we are going to go through or learn how to implement the Bayesian framework to regression models under the normal distribution, data that are assumed to be normally distributed. How do we formulate the Bayesian regression model for data that are said to be normally distributed? We will also look at how we will consider Bayesian regression under the Poisson, data that are said to be to follow the Poisson distribution. How do we formulate a Bayesian model to describe the distribution of the parameters? Then finally, we will also look at how we consider the Bayesian regression models when the data are assumed to follow the binomial distribution. So we are going to start with the Bayesian regression for the normal data. Bayesian normal regression. Others refers to the normal distribution as the Gaussian process. So let's consider a response random variable y. So the data of interest, our response variable is y. And here we are saying that y is normally distributed with mean, the design matrix of the covariate, which is x, and then vector of the parameter describing the covariates. Remember, when you fit your normal regression model, the expected equation is y equals to x beta. So the x beta, in fact, is your mean for the random variable. So the mean for the random variable is x beta. So we are saying under the regression analysis, y is normally distributed with mean x beta. And then the variance, of course, is going to be a matrix with zeros in the upper diagonal matrix and then zeros in the lower diagonal. So we'll have variances in the diagonal of the matrix. So we use sigma to represent the covariance matrix, the variance covariance matrix. So it is not always the case. So when there is correlation in your data, the diagonals of this matrix will not be zero. They will be values because there is correlation. However, if there is no correlation, the diagonals, the upper and the lower diagonals of this matrix will be 0, 0. It is only the diagonal that will have the variances in there. Now, the linear regression of y on the covariate x is defined in general as y equals to the intercept, which is beta naught, and then your predictors and their associated parameter estimates. And we add our random term or the error term. Here we are using UI to represent the error term. You can use your epsilon or your E to represent the error term. It doesn't matter, it's just notation. So we can generalize. So now we know that the data, which is Y, is normally distributed with mean X beta and variance sigma. Then how do we write the Gaussian or the normal distribution? You know, the normal distribution. So we are going to have the probability of the data given the covariate and the parameter, because the data is going to be described by the covariate, which is X, and then also the parameter estimates. And what is the distribution of Y? Y has a normal distribution. So we are going to have 1 over 2 pi, because this is the likelihood function. So we are going to have n over, because if you take the product, you multiply them, you take the likelihood, you take the product and multiply them, you are going to get n over 2. That is the square root, which is just 1 over 2. But if you multiply 2 pi to the power n over 1 over 2 times 2 pi to the power 1 over 2 up to n times, you are going to get n over 2. So this is going to be n root of 2 pi. And then here you have your sigma square. So here we are dealing with a matrix. So we have the matrix in here, and that is just the same as square root of the matrix. That's why we have the half here. So this is just square root of the variance covariance. And we are using absolute this because we can't have negative variance. We are just indicating that the variance, they are always positive. There is no negative variance. And then we have exponent. So you can see this is the same thing as our normal distribution function, but this time we are dealing with regression. If you remember in our previous lectures, here we used to have minus 1 over 2, and in the bracket we will have x minus mu. But this time our x is the random is the response variable y minus the mean. Remember, we always take the x minus its mean. This time we are dealing with a response variable y minus its mean. The mean is x beta. And remember, we used to square, because now we are dealing with matrices. We take the transpose of this. So instead of just putting a square here, we take the transpose of that, multiply by this guy here, and then we have the variance in here. So this is just like our sigma square, but here we are going to have the sigma squares in the diagonal. So it becomes what? A matrix with zeros in the upper and the lower part of the matrix. Now we have the other part. So this is just the same thing as writing this and then saying square. But here, because we want to express, so we have the transpose of this, and then we have the transpose, we multiply this by itself. And then we have the variance covariance matrix here. So this is just the same as our normal regression, our normal model when we are dealing with just a single variable. So here, that is our normal regression model. So this is the likelihood function for the normal data y. X is the design matrix, or you can say the covariate, because we are dealing with multiple linear regression here. So now let's move down. Remember, we are dealing with the Bayesian. We want to see how we can estimate the parameter beta under the Bayesian framework. So what that means is that now that we know our likelihood function for the data under the normal regression situation, Then we have to think of first, how do we obtain the parameters from this model? And this, you guys have done that already. So I don't need to show you how to estimate your parameters from this model. If you want to estimate your parameters from this model, what you have to do is to take log here. This part is just constant, so you can ignore that. Our focus is on this part. So you can take a log on this and then log on this. So the log on this is just going to, because you have exponent, so it's going to be ln. The natural log of this will just give you -1/2 and what is up here. You expand what is inside the bracket. Expand, yes. Yes. Yeah. I see. I'm just using the line cables. So if you take the natural log on this, the left hand side, and then also on the right hand side, then this is just going to be natural log of what is here, 1 over the whole of this, plus natural log of exponent of this. But you know the natural log of this exponent will just be equals to 1/2 of what you have here. So you end up with natural log of this equals to natural log of this minus 1 over that. So we expand the bracket here. When you expand the bracket here, you differentiate with respect to beta, and then you equate to 0 and solve for your beta. That is what you have done under estimation. But that is not what we are going to do here, or what we are doing here. What we are doing here is to find the posterior distribution for the parameters. So we need to know the likelihood function, the prior distribution for these parameters, beta. Then let's move on. So here, we can simply simplify the model here. So we have the sigma here, that is the variance covariance matrix here. So we can simplify that by just putting Zi to be equals to y over the variance, and then the m to be equals to the covariate over the variance. And that we just substitute our Z here. And then our m is going to be the covariate, which we just substituted here, and we have our beta. Now, you have done Taylor expansions, right? Have you done something on Taylor expansions? The first Taylor expansion, the second Taylor expansion. Have you done something on that? Can you guys hear me?
No, sir, please.
Hello?
No, sir.
Can you hear me? Hello, can you see the lecture slides? Okay, so we consider the general likelihood function, and then
Yes,
under
sir.
the Taylor expansion, we take log of the likelihood, so the natural log. So we are saying that the Taylor expansion, the natural log of the likelihood function of the parameters, the natural log equals to the natural log of the maximum likelihood parameter plus the derivative of the likelihood function with respect to the parameter estimates. And we have the beta, that is the parameter estimate minus the maximum likelihood parameter. This is supposed to be minus, not plus. Minus 1/2. the second derivative of the likelihood function with respect to the parameter. And then we have beta minus the maximum likelihood parameter square. So we are simply saying that in the previous equation, this part, we are saying that in this equation, we are just representing that part by this omega. So if we do that, then the equation or the likelihood function becomes this, because we are just taking natural log on the likelihood function. And if we do that, so we are going to have the natural log of the probability distribution here of the data condition on the parameters, natural log of that constant here, minus 1, because we've taken natural log, the exponent goes away, leaving only this part. So what we have to do is to expand what is inside the bracket now. If you expand what is inside the bracket, this is how it's going to look like. So you will take Z, and that is going to be Z prime or Z transpose. So Z transpose multiplied by Z. Then we take MB all transpose multiplied by Z. Then we take Z transpose multiplied by MB. Then we take minus MB all transpose multiplied by MB. If we do that, this is what we are going to have. Remember, we have ZMB, ZMB, two of them. Because look at here, we take Z multiplied by MB. Okay, we take Z, we multiply by MB. So we are going to get ZMB. And then here too, we are taking the MB multiplying by Z. So we have two of the MBs. And that is why we are having Z transpose Z minus 2 of Z transpose MB plus D transpose MB. This is what we have. So now we can differentiate this equation 3 with respect to beta. We can differentiate this so we can push our negative half inside. And then we differentiate with respect to beta. Let's do that and see. So if we push the negative 2 in and we differentiate with respect to beta, there is no beta here, so this goes to 0. There is no beta on the ZZ, this goes to 0. What is going to remain is these two guys here. So if you differentiate this part with respect to beta, this beta goes to 1. If you differentiate this part with respect to beta, the beta here goes to 1. So your equation will be simplified to ZM, Z transpose M minus B transpose M. And we equate that to 0. And then we solve for our beta here. So if you equate that to 0 and you are solving for beta, so what that simply means is that we are just taking the whole of this to the other side of the equal sign. So therefore, the beta is just going to be equals to the inverse of the M transpose M. And that is why we have the beta to be equals to M transpose M inverse, multiply that by M transpose Z. And when I taught you guys multiple regression and environmental statistics using the ordinary least square approach, this was the formula we had for the parameter, for the vector of the parameters. The same thing here. The M is your X. So change this to X, change that to X, change this one to X, and then change the Z to Y. Is it not the same? Our Z is the Y together with the variance, and then the M are the X's. Substitute that and see whether you will not get the same formula as we had under the environmental statistics when I taught you regression models and the multiple regression. So that is your maximum likelihood estimator. We haven't done Bayesian here. We are just doing estimation, which you guys have done before. So now, that means our maximum likelihood parameter is this. So that is just under the frequencies paradigm. Now let's think of it under the Bayesian paradigm and see. So under the Bayesian paradigm, now we know our maximum likelihood estimator. So here we have Z minus our M times the maximum likelihood estimator times the maximum likelihood estimator. So the M is just our X multiplied by the beta, the same thing. But here we are using the maximum likelihood estimator. And then, so this is the transpose, and then you multiply by this. This is the likelihood function for the data. What we are looking for is the posterior distribution. So we assume, yeah, there is no U here, so one U. So we assume a prior distribution for the parameters, and then we are using the conjugate prior for the normal distribution, which is the normal prior. So the normal prior for the parameters is proportional to the exponent of 1/2 beta. So this is the vector of the parameters, and this is the transpose of the vector of the parameters, and this is the variance associated with the parameter estimate. So here you can see that in the likelihood, we are using the sigma. Under the prior, we are also assuming a prior covariance matrix for the parameters. And in that one, we denote that variance covariance matrix with subscript beta. So this is the prior distribution for the parameters, or the vector of the parameter beta. So we have our likelihood function here. We also have our prior distribution for the parameters here. To get the posterior distribution, we multiply 11 and then 12 to get the posterior distribution. So we are simply going to multiply this guy here by this guy here, and that becomes our posterior. So now, the posterior distribution for the parameters beta, given the data X and Y, is proportional to the first part. So I'm just writing, so whether you write this or you write the other one, the same story. We are just substituting something. So you can write this or you can write the previous equation. It doesn't change anything. They are the same thing. So you can write this or you can write the previous one. Where is it? Yeah, you can use this. This is the likelihood function, or you can use this one, the same thing. It's up to you to use which one you want. So we multiply this by the prior. And you know, here is an exponent and here also is an exponent. So we are just going to have exponent of minus half, and then we have the rest adding them. So we are going to have minus half, then we put a bracket, and then so this whole part plus what we have here. So this is what we have. We multiply them. So when we multiply them, we are going to add, so we are going to have minus half, which is here, and everything is going to now be in one bracket. So minus half outside, because minus half is common here, and also is minus half is 1/2 is here, minus 1/2 is also here. So we are going to have minus half outside. Then we open bracket and put what is here plus what is here. And then we expand them. So if we are expanding what we have here, we expand what we have here. So here we are just saying that let V be equals to this one that we have here. So we simply sub, because we are trying to avoid writing long or bigger notations. So we just use the V to represent this one. And then we use K to represent the variance covariance matrix for the prior distribution of the parameters. Then we expand this. So if we are expanding this, we are going to have y transpose. This one, I'll multiply this and send it. It's not supposed to be, it's just x, not x transpose. So we take that, so whether x transpose or whatever, you get the same results. So we take y transpose multiplied by y. Then we take y again, multiplied by y transpose multiplied by this. We take x transpose beta multiplied by that. So when you do that, this is what you are going to have at the end. You have this at the end. Now, how do we find the mean and then the variance here? How do we find the mean and the variance here? We are going to use a trick that we use under the normal distribution when we consider just one variable. And the trick is what we call the kernel trick. So we are saying that in completing the squares, remember, y times y is a square. Y times y is a square. So in completing the squares, so this is going to be like when you have x squared minus 2x plus the constant. That is the same thing that we have here. So this will be square 2y, and then this is a constant. So in completing this square, we are given quadratic form defining the exponent terms in the Gaussian distribution. And we need to determine the corresponding mean and covariance. So we want to find the corresponding mean and covariance for the posterior distribution of the parameters. And we want to avoid computational complexity when we want to complete the squares. So to avoid that, we use what we call the kernel trick. The kernel trick. And how is that? To do that, we formulate a distribution that looks like the Gaussian distribution. You can see here we have y minus mean transpose, and then you have the lambda here, which is the same thing. So this here is the variance. The variance covariance is this symbol. That's why. So we use the sigma to represent the variance covariance. Here we are using the lambda to represent that. So we have y minus the mean. So this represents the variance covariance matrix, or the precision, if you like. So now we expand what we have here. So if you expand what we have here, you are going to have y. So here I'm just using the t to be transposed. Or so I think I'm just, this I could have just used, so this should have just be the prime, but I'm just indicating that this is the transpose because I'm using prime and I'm saying transpose. I think that's why I typed t here. So this is supposed to be transpose, which is just the symbol I'm using here. So t transpose, so is that the same thing as this one? So t transpose, t is used to denote the transpose. So we have y minus the mean transpose, and then the precision matrix, or the variance covariance matrix, we have y minus the mean. So if we expand this, y transpose multiplied by the precision matrix multiplied by y. So we are going to have y transpose times the precision matrix times y. Then we take y transpose multiplied by the precision matrix multiplied by the mean. And when we do that, then we take also the mean transpose multiplied by the precision multiplied by y. So if we do that, we are going to get minus 2y transpose the precision matrix times the mean. And then we take the mean transpose times the mean. So this is minus mean transpose multiplied by the variance covariance matrix multiply that by minus mean. So that is going to be positive mean transpose, the variance covariance matrix, and then we have the mean. So this is the same thing as this. So the whole of this, y is the variable that is varying. So here we have y prime, the precision matrix, y, minus 2y precision matrix of the mean. This part is constant. So we just say plus constant. Now compare what we have here with what we have here and see how you are going to find your mean and your variance. Now let's go down. The precision, look at the precision. Here, so y is acting like our beta here. Y is acting like our beta here. Now compare this with where we have beta prime and then the beta. So beta prime and then the beta. Here we have beta prime and then we have beta here. You can see this is similar to what we have here. Beta prime, y. So here we have beta prime over there and then we have prime. And there is something in the middle. Y prime and then y, or y transpose y. But there is something in the middle. Go back to that equation. You can see that we have beta prime or beta transpose, and then we have beta here. And we have something also remaining in the middle here. So what is remaining in the middle here is equals to the precision matrix. So the precision matrix, which is here, is going to be similar or is going to be equals to what we have here. That is what is in the bracket here. So this is y transpose, this is y, and what is remaining is this one. So the precision matrix is equally or is simply equals to what we have. And that is the precision matrix here. And that is the variance covariance. Now let's look at how we get the mean. Well, how do we get the mean? Now the mean is here. This is the mean. And we have minus 2y transpose that. Now go back to this equation. Look at here. We have minus 2 beta transpose. And then here we have minus 2 y transpose. What is remaining is the precision matrix and the mean. So in that equation that we have in the previous slide, what that means is that you have 2 beta transpose. So the 2y transpose here is equals to that 2 beta transpose. So that means the precision matrix and the mean is equals to X transpose the variance covariance matrix. We are using this to denote that, which is the same thing as that, multiplied by Y. So our mean is going to be equals to, our mean is going to be equals to X transpose the variance covariance matrix. I'm just using this one to denote that. The variance covariance matrix and Y. So our mean, our variance covariance matrix, the one I've highlighted here, and the mean, they are equal to the X transpose. They are equal to the X transpose variance covariance matrix and the Y. So if you equate this to that, so that means that our mean is simply going to be, because this is mean, the mean and the precision is equal to the X transpose V and the Y. But we want only the mean, so we divide both sides by the precision matrix. So that's why we have the precision matrix in here. We want the mean because the mean times the precision matrix is equals to V, X, and the Y. but we want only the mean. So we divide here by the precision matrix, divide here by the precision matrix. And that's why we have the precision matrix to be here. So now we have the mean, or we have the posterior mean to be the precision matrix multiplied by, so this is the precision matrix for the data, multiplied by the precision matrix for the prior, multiplied by the transpose and the response variable. And our precision is given by this. In general terms, what that means is that our posterior distribution of the parameters is normally distributed with the mean, with the parameter beta, given the mean and the variance covariance. So our variance is this guy here, and the posterior mean is what we have here. Now, the maximum posterior, so that is the maximum posterior. So now we say the mean is equals to what we have here. The mean is here. The mean is here. But we know that this is equals to this one here. The precision matrix is equals to this one. So we can substitute that. So if we substitute that, this is what we are going to get. And now the V that we are seeing here is sigma. That is the sigma that we have here. So wherever we see the V, we replace that with the sigma. And that is going to give us sigma, which is the V here. And then we have it also here, which is here now. Then we have our X transpose X plus our K. But remember, we said the K is the precision matrix or the variance covariance for the prior. And then we use the I to indicate that the variances are in the diagonal, not in there is no correlation. And then finally, we have our X transpose and then Y. Look at this. Is it not the same as what you have when we did the normal, when we did the multiple linear regression using the ordinary least square? They are the same. The only difference is that we have plus this guy here. And that is because we have the prior information. Otherwise, it would have just been only this part and then your variance and your XY. But because we have the posterior, that's why we have the posterior variance coming in here. Otherwise, we will just have just this part and that part. And then remember, it's X transpose X all to the X transpose X inverse multiplied by X transpose Y. That was what you know in the multiple linear regression situation. Now, so we now know that our maximum posterior is given by that. So the maximum posterior of the parameters, we can denote it by this, and that is just equals to this. And this is the variance covariance matrix. So our posterior estimates are defined as this. So the posterior or the maximum posterior, the posterior parameters, the posterior mean is defined by this, and the posterior variance is defined by this. So we know our posterior mean and our posterior variance. So if I know my prior variance and I know my prior mean and I supply them, at the end of the day, this is what I'm going to get. So I need to know my X and I need to know my Y. And remember, under Bayesian, so we need to supply this information, the initial information, and then we simulate the parameters until convergence will occur. And that is why I said we'll be doing these things next semester. So in general, or at the end, what that means is that the posterior distribution for the parameters, they also have a Gaussian distribution, and that is defined as 1 minus 2. So now we have the parameter beta minus the maximum likelihood parameter, then the precision matrix. So this is the transpose, and then we multiply it by that. This is Gaussian. So all that I need now is to supply my initial values for the parameters. Then I will simulate to get the posterior parameters. So I will simulate until the convergence of the chain will occur. So this is the part that I will need to do my simulation. And that is the Bayesian regression model under the normal distributed data. Any question? Any question? All right, so let's move on. Now we are going to look at a situation where we have data as counts. We are counting the number of newborn babies, the number of diseases, the number of COVID-19 cases per day or every month. We are counting numbers. And when data are count, then we can assume that they have the Poisson distribution. But then how do we do that under the regression model? If we want to estimate the risk of disease in a given area or in a given region or in a given country, how do we do that under the Poisson regression? So suppose that the unknown risk in a given of a given disease in a particular region is denoted by this. So we have region 1 up to region n. So each region will have its associated risk denoted by this. And now let y and then n to denote the number of disease cases and the population at risk. So the number of disease cases and the population at risk in region I. So n is the population, y is the number of diseases. And the number of diseases, we are saying that it follows the Poisson distribution. Now, the expected number of cases in region I is R multiplied by the population at risk. R is the proportion, the probability of getting the disease. Remember when you did your probabilities, if you are given probabilities associated with given items, and you multiply the probabilities by the number, then that gives you the expected value. So we need to know the probabilities associated, the probability of getting the disease for every region, multiplied by the population of that region, and sum them up, and that will give us the expected number of cases. So here in general, overall, we sum the cases for all the regions and divide by the total population. And that gives us the R. And we multiply that by the population. And that will give us the expected number of cases. Now, under the frequencies paradigm, under the frequencies framework, if we know that the data follows a Poisson distribution, remember when a data follows the Poisson distribution, we have the rate, which is always denoted by lambda. But in this case, our rate is the variable that we have here. We have the theta that we have here, and then multiply by the expected number of the diseases. So the rate in this case is the risk multiplied by the expected number of cases. So our rate is equals to the expected number of cases multiplied by the risk in the, so we are going to the expected number of cases in region 1 or region I multiplied by the risk in region I. This is our rate, not lambda anymore. So what is our likelihood function? Our likelihood function, so we are saying that based on sample observations, y1 up to yn, the likelihood function and the corresponding log likelihood function are expressed as this. So the likelihood function is the product of x to the power e. So this, you remember the Poisson distribution is exponent of the parameter, the lambda, which is the parameter describing the Poisson process, and then the parameter describing the process to the power the data, which is usually x, but this time we are using y. Divide that by factorial of the data. So this is the Poisson distribution, and here, because our lambda is now expected number of cases in region I multiplied by that. So that's why we are substituting that here. Otherwise, it was just going to be exponent of lambda, exponent minus lambda, and then lambda to the power y divided by factorial of y. But our expected, that is the lambda, is now expected number of diseases multiplied by that of the risk. Now, if we take the log likelihood, the natural log of the likelihood function, then what that means is that, remember, so we are going to have this multiplied by itself up to n times. So if we do that, then we are going to have summation here, because we'll be having exponent of this times exponent of that. So we sum them, and then that is the part here. And then here, we are going to sum the y's. So in the end, the log likelihood of this is going to be, because here is exponent, so the natural log of that will just be minus summation of expected values, expected number of cases in region I, multiplied by the risk in region I, plus this is going to be natural log of this to the power y. So the y goes down, so which is going to be summation of the y, natural log of the expected number of cases multiplied by the number at risk in region I. Minus, remember this is here, so is the same, you take the log, so the division is going to be minus of this. So this is supposed to be minus ln the natural log of this, but I didn't bring that. So this is supposed to be log of the product of the y. But we are not interested in the product because it's constant. So when we take the derivative, this one will go to 0. So we are not even interested in it. When we take derivative with respect to our number at the number at risk, then this one just goes to 0. So we are not even interested in this guy here. Now we differentiate equation 22 with respect to the parameter of interest, which is the theta, which is the theta here. So we are differentiating this equation 22 with respect to theta. So the maximum likelihood estimator is denoted by this, and it is estimating theta. And we obtain that by differentiating 22. We are taking partial derivatives of the likelihood function, the natural log of the likelihood function with respect to theta, and equate that to 0. So if we do that and equate to 0 and solve, then we are going to get the risks at each region to be equals to the number of cases in region I divided by the expected number of cases in region I. And usually you guys will hear people say standardized mortality ratio. So this is the measure of standardized mortality ratio. So once I'm able to estimate this, I can tell which region has higher risk than the other region. Once I know the number of cases in region 1, and then I know the expected number of cases in that region, then I should be able to find the risk associated with that region. And that is what we call the standardized mortality ratio in region I. If we want to get the standard error associated with this, that is simply going to be the square root of the number of disease in region I divided by the expected number of the disease in region I. We can also find the corresponding confidence interval associated with that. And that is going to be the maximum likelihood estimator plus or minus our Z value, which we read from the table. And then we multiply that by the standard error that we have estimated here. And that will give us the confidence interval. Now, how do we do that? And so this is just the likelihood function. So I haven't gone to Bayesian yet. This is just the frequentist way of doing things. The frequentist way of doing things. You find the likelihood function and you can differentiate directly, or you take log of the likelihood function and then you differentiate. So after taking the likelihood, you can decide to differentiate right away. Or you just take the likelihood, the natural log, or the log likelihood of the likelihood function, and then you differentiate with respect to the parameters, and then you equate to 0 and solve for your maximum likelihood parameters. And that is what you guys in the under the frequentist framework or paradigm. Yes. So that is what you guys know under the frequentist paradigm. Now let's look at how we do this under the Bayesian paradigm. We need to know our prior distribution for the parameter, that is the disease at risk, the disease, the risk of disease at region I. We need to know what is the prior distribution for that risk in region I. And then once we know the prior distribution for the risk in region I, then we multiply that by the likelihood that we know here and see how the posterior is going to look like. So we say that the posterior distribution is defined as the probability of the parameter given the data. So this is the vector of the risk for each region. So we are just using the bold theta to denote vector of the diseases, the vector of the risk of disease for all the regions or the areas we are studying. Given the data, so the probability of the risk in all the regions given the data is equals to the data likelihood, which we have described in the previous slide, multiplied by the prior distribution for the parameter of interest. Then we integrate that, which is the marginal density. So we integrate with respect to theta, and that will give us the posterior. And remember, We said when you integrate and you approaches the maximum likelihood parameter, this guy here becomes 1. And we refer to it as the normalizing constant. So when you integrate and this one gets to 0, then the parameter estimates you sample from the distribution remains the same. They don't change anymore because this gets to 1, and that means whatever you are doing has converged to the true value or to the maximum parameter. So you will not get anything different from that parameter. So we need our likelihood function, and we need our prior function for the parameters in order to be able to find the posterior. Back to our disease. So here we know the number of cases for each region I, the expected number of cases. So we said that Y denotes the observed number of cases, and then E denotes the expected number of diseases in region or county or country or area. And then the Y is normally distributed with rate expected values multiplied by the risk. And that is what we have here. This is the same equation we have in the previous slide. Now we are assuming that the risk for each region has a prior distribution, and that distribution is the gamma distribution. Remember, the gamma distribution is a conjugate prior for the Poisson distribution. Conjugate prior in a sense that if we multiply the gamma prior by the Poisson beta, the resulting posterior distribution is going to be gamma. So the gamma distribution for the parameter of interest, that is the risk of disease, given our alpha and then beta, I just use A and B, is the risk alpha minus 1, gamma of alpha and then B to the power alpha or A. And that is going to be exponent of alpha, that is the risk B. And this is what we know. This is what we know. This is what we know. So that is the gamma. We've seen this distribution when we're dealing with a single variable or a single parameter. And we are seeing it here also. So we are just replacing our X or our theta that we use to indicate there as this one here. So we now have the prior distribution, which is this one. We also have the data likelihood, which is here. Then we multiply them. So if we multiply them, so the likelihood function, so we take the product of the data, so the expected cases and the risks to the power. So this is the lambda to the power y, exponent of the lambda, exponent minus of the lambda, and our lambda is E, that's the expected cases multiplied by the theta. The theta is supposed to be I, but I didn't indicate that, so it's just supposed to be theta I. Multiply that by the prior distribution, which is this one here. So you can see that what we have here, we divide by the integral of all of that. And this goes to 1. So we can simply write this as proportional to what is at the top and ignore the down part. So if you consider this model, for instance, the theta that you have here. So if you just assume that the whole of this place is theta, and then the whole of this place is also theta, you can see that this theta and this is going to be the same. So you are going to have theta alpha plus yi minus 1. And then the exponent here is going to be exponent of theta. So it's going to be exponent minus open bracket of the theta plus theta. That is exactly what you are going to have. So when you have that, you can simplify that down. So what we are simply going to say is that we now have our beta star and then A star. And we are saying that A star is summation of the summation of the number of disease cases plus our A here. So which is the same thing as what we have here. So we are going to have our theta, which is going to be alpha plus y here. So our alpha is now going to be yi plus a, and then our beta is going to be expected number of cases, that is the summation, plus the beta. So we know our alpha, and we know what our beta now is, just like we did under the single parameter case. So what that means is that we now need to go and substitute these values into the expected value for the parameter and the expected value for the value. So the expected value for the parameter, we go there and substitute our alpha and then substitute our beta, and that will give us the expected value for the parameter. Then we will also go to the variance and substitute our alpha and also substitute our beta to get the variance, the posterior variance for the risk of the disease. Now the question is, remember in the previous slide, so the question you ask yourself, what is the expected value or what is the expected formula for the parameter estimates? So if you remember, the expected value for the parameter is the alpha divided by beta when we consider the Poisson gamma. So the gamma mean is alpha over beta, and then the variance is alpha over beta squared. You remember that? So now that we know our alpha to be summation of the disease in region I plus the alpha, then we substitute that in place of alpha. And in place of beta, we substitute this. So this becomes our posterior mean for the risk of the disease. Now, for the variance, we know the variance is alpha over beta squared. So our variance, the posterior variance for the disease risk, is going to be summation of the number of diseases in region I, the number of disease cases in region I plus alpha, divide that by summation of the expected number of disease cases in region I plus the beta, all squared. And this becomes the posterior variance. So once I know the expected number of cases and I know the value for alpha and the beta, the expected number of cases, then I should be able to find the corresponding posterior variance. So I will need to supply my beta and I need to supply my alpha, and then supply the data and then the expected cases in order to find my posterior mean for the relative risk or the risk for each of the region and the associated variance of the risk for each of the regions. And that is what we have here. This is just further different ways of expression, the expected mean and then the expected variance, and then the variance of the posterior parameter, the risk of the disease in region I. Now you've seen what we have done here. This guy has just, I mean, I don't know what he has done to, look at what he has drawn on the slides. These students are very funny. Voice. Sit down and listen to lectures. You just pushing things around. Can you see the slides? Hello, can you see the slides? Can you guys see the slides?
Yes, sir.
All right. One of you was drawing things on the slide. I don't know what was happening.
Yes, sir.
So I've removed him. So let's continue.
Okay.
So now you can see that what we have done in that previous slide hasn't, I mean, this have not taken into account the regression aspect. We want to look at how do we pull in the regression aspect into this model? How do we get the relative risks to be in a form of the parameters, beta, and all that? And to do that, we start with what we call the log normal model. So the same description for the data. We have our number of disease in region I, then the expected number of cases in region I, then the risk in region I or the relative risk in region I. And the log normal is defined. So we say that Y, it has a Poisson distribution and the expected. So you see the expected number of cases is here. And this time we have exponent of eta. We call this symbol eta, exponent of eta. So instead of saying the relative risk of the disease, we are replacing the relative risk of the disease by exponent of eta. So where I'm saying that where the relative risk of the disease in region I is equal to the exponent of the eta. We are trying to find a way by which we can relate the risk to the covariate. If there is a high risk in a particular region, what are the variables that are probably causing the risk in that region to be high? So we want to build the regression in there. So we introduce exponent of eta in place of the relative risk of the disease. And that, what this simply means is that our rate, which is going to be what the whole of this thing here for the Poisson, is now going, so let's say we are using the mean I to represent the rate that would have been here. So what that means is that our mean I, that is the rate of the disease in region I, to now be equal to expected number of disease cases multiplied by the exponent of the eta. What name under regression, the name that is given to the eta, you call it what? Linear predictor, right? So the eta is the linear predictor. So the eta, you can look at it like beta naught plus beta 1x plus beta 2x2 plus beta 3x3 and so on. So that is where the regression is coming in. So we are having expected cases instead of multiplying it by the relative risk, but we substitute the relative risk now with exponent of eta. And this eta is a linear combination of the parameter estimates. Now, so fitting a generalized linear model with a log-link function. So we are saying that we are fitting a generalized linear model with a log-link function. So generalized linear model, we can fit, using the generalized linear model, we can fit data that is normally distributed, that are normally distributed. We can fit data that are Poisson in nature. And then we can fit data that has a binomial distribution as well. So we are saying that fitting a generalized linear model with a log-link function, we then take log of this guy here, and that is going to be log of the rate of disease in region I equals to log of the expected number of cases in region I plus eta, because this is exponent. So taking log of that, that is the natural log of that, we get that. So this is log base E. This is log base E. Or you just write natural log. That is the ln of this, and then the ln of the expected cases. And then the ln of the exponent of this is just this, which is eta. So this eta is in fact equals to beta 1 plus beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 and so on. So by the Bayesian framework or paradigm, we assume that the eta has a normal distribution with mean and precision, which is tau squared. And we are saying that the mean also has its distribution. So remember, we always have parameters. So the parameters in this case, so this one has a distribution. So the mean has its distribution, and then the tau, that is the variance, will also have its distribution. So here we are saying that the parameters, that is the mean, is normally distributed with mean and then variance. And we are saying that the variance of this guy here has a gamma distribution with alpha to be half and then the beta to be 0.05. Now, if we then consider a situation now where we want to show our covariate or the design matrix of the risk factors, then we are going to say that y is conditional on, so that's the likelihood function, is conditional on the expected number of cases, the risk factors or the covariate, and also the betas. And we said that they are y is independent and it is distributed as Poisson with expected cases and the exponent of the eta. So the eta, as I've said, is just the same as beta naught, and then we generalize that. So summation from P1 up to P. So beta 1, beta 2 up to beta P. And this is a link, is the linear link function or the linear predictor. And that we have the U here, and the U are the residual random effects, and that captures the residual unexplained log relative risks in region I. And we denote tau to be the variance or the precision associated with the residual variance. And remember, under linear regression, we always say that the variance of the residual is constant. So, okay, this is just a repetition of that, I think. So what that means is that our log of the relative risk, is equals to this, equals to what we have here. So what that means is that if I divide both sides by log, then I'm just going to have my relative risk or my risk of disease in region I to be equal to exponent of the whole of this thing here. And that is what we are having here, exponent of beta naught plus beta 1 x1 plus beta 2 x1. That is why I just sum them up here. So you can now see how the risk of the disease is going to be affected by the risk factors. So the beta 1 are these are the regression parameters. The beta naught is the intercept or the overall risk effect. So hence the mean of the Poisson distribution is going to be equal to the expected cases multiplied by the exponent of the eta. And that is the same thing as E, that is the expected cases exponent of the eta, which is what we have here. And that means if we take log on that, then we are simply going to have log of the rate of the log of the cases in region I, the risk of cases in region I, log of the expected cases, and then we have the linear predictor here. So how then do we carry out our parameter estimation? We need to know the likelihood function, which is here. We said that it has a Poisson distribution. So we are now going to have the whole of this is our lambda to the power y, exponent of lambda divided by factorial of y. So here our lambda is e exponent theta to the power I, exponent of minus theta, which is expected cases, and then exponent theta, eta. And that means we need to know the data, we need to know the expected cases, and then we formulate our likelihood function. So you can see in this, we need to know the distribution of the risks, that is the prior distribution for the relative risk. We need to know the prior distribution for the parameters beta. We need to know the prior distribution for the residual term here. So here I'm saying that we will need the prior distributions for beta as well as the U. And once we know that, then we can get the posterior distribution for the relative risk. So we need the prior distribution for the relative risk, we need that for the betas, and we need that for the residuals. And we've already noted that the risk has a gamma distribution. The beta follows the normal distribution, and then also the residuals we know follows the normal distribution as well. So we are going to have normal distribution for the parameters and also a normal prior for the residuals, and then we are going to have a gamma distribution for the relative risks in the regions. So 3 prior distributions here. So the prior distribution for the parameters we assume has a normal distribution. So here we have 1 because we are taking the likelihood. So we have the number of parameters p over 2. So depending on the number of parameters. So if you have 3 parameters, so you have that. Because we are going to take the product of these things. So we have p times divide by 2. So that is just the p root, the pth root of the whole thing that we have here. And then we have the variance for that, and that variance, which is the tau here, multiplied by 1 minus 2, then we have beta squared over the variance. So this is the beta, this is the parameter over its variance. And then the prior distribution for the random effect, so we are using n. Remember the variance, the p, the parameters are up to p, and then the residuals are up to 10, are up to n, because the residuals, they are equal to the number of areas that you are dealing with, or the number of people that you are dealing with. So we have n over 2 that, and then the variance for the residual is tau u, and all that to the power n. Exponent, so here is supposed to be 1 over, okay, so I've just pushed the 2 inside. So you can see that 1 over 2, I'll push that 2 inside, so I can bring it out to be negative 1 over 2 is the same thing. Ui squared, divide that by 2 tau u squared. So this is the prior distribution for the beta, and this is the prior distribution for the random effect. So therefore, our posterior distribution is going to be the product of the likelihood function that we have here, that of the parameter estimates, and that of the residuals. And therefore, we multiply them. When we multiply them, now the beta here has its parameter here. The u here has its variance here. So that means we need to also define the distribution for this one and also for this one. So we multiply this by that and also by that. So if we want to simulate this to find our beta, to find our u, to find our tau of the beta, and to find the tau or the precision of the residuals, then we need this one should go, this one should be on the other side, not here. This is the risk of the disease. It should be here, not here. So we multiply this, and this is what we have. So this is what we have to simulate. So I have to supply my expected number of disease case in region I. Then I need to formulate my linear combination of the parameters, and I have to supply the data. I have to supply initial parameters for, or the distribution for my u, that of my betas, also supply the distribution for the tau, supply the distribution for the tau u, and that will enable me to estimate the parameters or the posterior parameters from this model. So just like I said, the prior distribution for the linear regression coefficients are, so the beta we said is normally distributed mean 0, and then the variance tau beta. And but because we said this is normally distributed with mean 0 and then tau square beta, Then the corresponding conjugate prior for this, we said that it has the inverse gamma distribution, and that is defined by what we have here. This is the inverse gamma distribution. We have the psi to the power omega over gamma of omega, then the variance or the precision of the parameter to the power minus of omega plus 1, exponent of minus psi over the precision of the parameter. And we are saying that these parameters, whatever values they are, should be greater than 0. If this is 0, this becomes undefined, and the whole of this becomes undefined. If this is 0, then we get 0 here, and the whole of the function becomes undefined. So we are saying that the precision, the omega, and the psi should be greater than 0. So the equation 38 is the hyperprior distribution for the precision of the parameter beta with the hyperprior parameters, omega and psi. So we defined the parameter, the precision for the parameters, that is beta, to have gamma distribution defined by that. And then the residuals to have a normal distribution with mean 0 and then variance that. And then that of the variance of the residuals to have a gamma distribution defined by this. Once you specify this, then it becomes easier to formulate, to simulate the parameters from the posterior distribution. Any question? Any question? All right.
No, sir.
Okay, so this is where I'm going to end my lecture. And we'll meet face-to-face meeting. We will have our face-to-face meeting. Is it tomorrow or Friday? Hello?
Sir, please tomorrow.
So we'll have our face-to-face meeting tomorrow and see what we can do. So read through the slides. Wherever you have difficulties in understanding, then you can raise those questions when we meet in our face-to-face meeting. So you read over wherever you have difficulties in understanding. We meet in the lecture, you can raise them, and then we'll quickly discuss them through. So when we meet in our lecture, in our face-to-face, when we meet face-to-face, then we'll go through the binomial distribution and then see how that is also formulated. So the statistics students next semester will implement these models in a software. So we'll apply them to real data and then see how we simulate the parameters from these models that we have defined here. So if you have no questions, then we'll end the lecture here. I will save the recording of this meeting, and then I will share that in the YouTube channel so that you guys can go and then follow the discussion if there is something that you couldn't get well during the lecture. Probably when you go through the video, then probably you'll get some understanding. And
Okay, sir.
if you are not able to understand, then face-to-face meeting or in our, yeah, we are almost, I mean, through with the course, but that is not the end. We'll always have our Zoom meeting as usual. We'll have our face-to-face meeting as usual. And the purpose of that is to go through what we have done so far and to see where we have problems so that we can discuss them together. So now the ball is in your court. You have to study the lecture material and come out with areas that you have no understanding in. Because I will not come and be teaching you again. You have to come to the lecture and say, oh, sir, can you go over this again? Or, oh, I have problem understanding this part. Yeah, don't come and tell me to go through over a whole thing. Yeah, get what you are doing. Then you say, oh, this part, this is where I got to, but I don't know how